everyone. Welcome to Alan Digital Classes. Today we are going to discuss a very important subtopic in inorganic chemistry under the P block elements. We are going to discuss about back bonding today. But before that, can you people tell me what do we mean by a Lewis acid? A Lewis acid is an electron pair acceptor. Why does it have to accept an electron pair? Because the central atom's octet is not complete. Just take the example of BF3, in which boron is too short of electrons, means it's short of an electron pair to complete its octet. It has only 6 valence electrons around it. So BF3 will act as a Lewis acid. Now tell me, if I compare the Lewis acid strength of BF3 versus BCl3, in BCl3 also boron is electron deficient, it will also act as a Lewis acid, but both BF3 and BaCl3, do they have the same Lewis acid strength or different? What do you think? What is the deciding factor, or better I can say differentiating factor? Yes, it is the back bonding concept which we are going to discuss today. One more aspect can be analyzed with the help of this back bonding concept, the Lewis base strength. Lewis bases are electron-rich species, and the greater availability of the lone pair of electron on the nitrogen atom indicates greater Lewis base strength. So, if that lone pair is not present on that atom and goes where, we'll find out. Does it affect the Lewis base strength? All these aspects we are going to cover in today's discussion. Here we go. What is a back bond? It is a coordinate bond which is formed between two adjacent atoms of a molecule, and that takes place by the sideways overlap of an orbital which is completely filled or fully filled and the other orbital which is vacant. I repeat, it's a kind of coordinate bond which is formed between two adjacent atoms in a molecule in which sideways overlap takes place between a vacant orbital and a fully filled orbital. So is it going to be an intramolecular thing? Yes, it's going to take place within the same molecule in an atom. Also, this type of coordinate bond takes place by sideways overlap. Remember the word sideways. So what kind of bond is that? Yes, it's a pi type of coordinate bond. You can call coordinate bond as dative bond also. Hence, it's a type of coordinate bond which is pi type. You can call it dative or coordinate. Why did I say pi? Because as I just now mentioned, it's formed due to sideways overlap. Wait, sideways overlap, which means already one sigma bond must be there between the two bonded atoms in a molecule. Yes, and yes, it's an intramolecular concept. So this kind of back bonding is seen between two adjacent atoms present in the same molecule. Conditions for back bonding. Students, one condition is already mentioned there, but the first and the most basic condition is the presence of a covalent bond or a sigma bond which is already present. And out of the two atoms, one must have a vacant orbital to accept electron pair, the other must have a filled orbital to donate the electron pair. And this sideways donation would be more compatible if the orbitals are small in size. If it's a 2p-2p overlap, you will see that the bond which is formed would be much stronger. Yes, I know I'm talking about a pi bond which is relatively less stable than a sigma bond, but in that pi bond also, which is formed by the sideways overlap. Imagine AlCl3, 3p of Al and 3p of Cl. They are too large, students. So in that case, that would not form an effective pi bond. So I would definitely prefer that at least one of the atoms would belong to the second period, because the 2p overlap with another 2p would be best, but another 3p or another 3d also, basically we'll see pd overlap also, would be sufficiently compatible. So there should be a covalent bond between the two atoms, as I was just talking about, the sigma bond, which should be definitely present. One of the atom must have a lone pair. Think of BF3, think of fluorine already having a lone pair in its p orbital. Think of boron having a vacant orbital. And it's very good if both the atoms belong to the second period, so that their p orbital overlap could be quite effective. But if at least one of the atoms also belongs to the second period, and let the other belong to the third period, let it be 3p or let it be 3d also, not a problem. Good enough compatibility is seen in those cases also. Fine. So these are the conditions for back bonding. So right now what we learned is what is a back bond. Let's quickly revisit. It's a type of pi-coordinate bond which is formed between two adjacent atoms in a molecule, which are formed by the sideways overlap of a filled orbital with another vacant orbital. For better compatibility, if at least one of the atoms belong to the second period and the other, good if it's of second period or at least of the third period, let it be 3p or 3d, the compatibility, the bond strength would be sufficient for the formation of a back bond, a strong back bond. And which of the following back bonding is present? Let's see. BF3, PF4 minus, trisilyl amine, NF3, AlCl3. Let's analyze the first one, BF3. As just now mentioned, we will see that boron here has a vacant p orbital. Fluorine has a filled p orbital with a lone pair to donate electron via sideways overlap. Both the elements belong to the second period, perfect example of back bond. And let's see how this back bond is formed. So here we are discussing about the back bonding in BF3. It's p-pi back bond. So here boron is sp2 hybridized, and you can see that fluorine's lone pair is donated to the vacant orbital of boron. Wait, only this fluorine will donate? No. What about the other fluorines? So it's also possible that not only this particular fluorine and boron form a back bond, it's also possible that either of this or this fluorine forms a back bond. As you can see here, this fluorine can also form. Why this fluorine will be left out, students, then? No. It can also form a back bond. Does this mean all the three BF bonds in boron, the bond length lies in between a single and a double bond due to this kind of back bonding? Or if you imagine such kind of resonating structures where there can be a double bond between this BF or this BF or this BF. So the actual structure, the actual bond length lies in between a single and a double bond. Does this mean back bonding increases the bond strength, the bond order, and decreases the bond length? Yes. Can you comment on the hybridization of the boron before and after back bonding? Boron was sp2 hybridized before back bonding. After that also, boron's hybridization remains unchanged because the bond which is formed is of pi type. So pi bonds are not considered under hybrid orbitals, you know that well, right? So the hybridization of boron remains unchanged even after it forms back bond. One other important thing is to be noted that Due to this back bonding, boron is no longer that much deficient in nature, as a result of which its Lewis acid strength is affected, is decreased. Greater the deficiency on the central atom, greater will be the Lewis acid strength. Back donation or back bonding decreases this electron pair deficiency. Hence, it decreases the Lewis acid strength. So, both the atoms belong to second period, as I had just now mentioned, and hence 2p pi back bonding is same. Yes, as one of the back bonds is shown here with this followed by this, and right now this fluorine atom. So, back bonding increases bond order, bond strength, decreases the bond length, and decreases the Lewis acid strength of BF3. Next, we are going to discuss about p pi d pi back bond. Let's take the example of tricylyl amine. The lone pair which is present on this nitrogen atom can be donated to any one of the vacant d orbital which is present on the silicon atom. So, you have here, here or here. Free silicon atoms. So, this back bonding is possible either between this silicon and nitrogen, or this silicon and nitrogen, or even this silicon and nitrogen. As I had just mentioned. So, this means, what do you think? Is that lone pair actually available on the nitrogen atom? Is it actually present in a hybrid orbital? No. Due to back donation, this lone pair is not present on the nitrogen atom. It's present on any one of the 3d orbitals present on these silicon atoms. So, the hybridization of the nitrogen atom here is sp2 instead of sp3. Make a note. If the lone pair is involved in back bonding, it will not be considered to be present in a hybrid orbital. So, what you have is 1, 2, 3. That's it. This would not be considered to be present in a hybrid orbital. So, the nitrogen present here is sp2 hybridized. So, yes, in this particular case, there is a change in hybridization which is taking place due to back bonding. So, I would like to repeat, in the previous case, the central atom had a vacant orbital. That vacant orbital was accepting electron due to back bonding. There was no change in the hybridization observed due to back bonding. But here, the central atom contains a lone pair, and that's being given to any one of the silicon atoms here for back donation. So, in this case, the lone pair is not considered for hybridization. Its hybridization changes due to back donation. Fine. So, nitrogen here is sp2 hybridized. It is planar in geometry. And greater the availability of the lone pair of electron, greater is the Lewis base strength. In general, you know that, right? But here the lone pair is busy in back bonding. Is it available? Definitely not. Hence, the Lewis base strength decreases here due to back bonding or back donation. So, here you can expect a 2p donating to the 3d of silicon. 2p of nitrogen donating this lone pair to the 3d orbital of silicon atom. As a result of this, you can clearly see that all the 3 bond lengths lie in between a single and a double bond. The bond order increases, and so is the bond strength, and the bond length decreases as a result of this. This is the planar geometry of tricylyl amine, and the back donations are shown when nitrogen is the giver, the 3d orbital of silicon is the acceptor. Effect of back bonding, just now we saw on geometry, on hybridization, on bond order, bond length, bond strength. Bond order increases, bond length decreases, bond strength increases, the Lewis acid character changes. So I just now give an example where BF3 due to back donation or back bonding is no longer that efficient, and hence the Lewis acid strength decreases. The Lewis base strength of tricylamine decreases because the lone pair is no longer available. Geometry. Okay, first hybridization. Hybridization is changing if the lone pair is involved in back bonding. If the central atom has vacant orbital in that particular case, say for example in the case of BF3, hybridization does not change. Geometry doesn't change in the case of BF3, while it changes in the case of tricylamine. So it's correctly written in both these places that hybridization may or may not change, geometry may or may not change. Yes. Now a question for you. In which all cases do you see that the BF bond strength is maximum? Since we are discussing the concept of back bonding right now, they are indirectly asking us in which case do you see a back bond which in turn increases the bond order and bond strength. And tell me, since we discussed it right now. Yes, you are right. It is BF3 which shows back bonding, due to which the BF bond strength and bond order is more. In BF4 minus, boron already has a complete octet. And remember, boron belongs to the second period. So it can have only 8 electrons around it. Fluorine has lone pairs around it, agreed, but boron doesn't have any vacant orbital to accept those electron pairs. So you don't see back bonding in the case of BF4 minus here. At the same time, NH3 dot BF3. So I have NH3 which has a lone pair and you have BF3 which has a vacant orbital. So, if they form a complex or a bond, you can expect nitrogen to be the donor and boron to be the acceptor. A coordinate bond, but a sigma type, as you can see, is formed from nitrogen to boron, but no back bonding is seen. And hence, since back bonding is seen in the first case, so the BF bond strength is maximum in the case of 1. Fine. Now, this reminds me that we should go back to the list where they were asking us which of the following shows back bonding. In the first case, yes, we saw back bonding possible. I just now explained not possible here. We just now saw a back bonding, a change in geometry as well as hybridization in this particular case. Yeah, both fluorine as well as nitrogen have a lone pair. Nitrogen doesn't have a vacant orbital, neither fluorine, to accept lone pair. So, back bonding not possible here. Now, let's take the last case in which aluminium has a vacant 3p orbital. Chlorine has a filled 3p orbital, but 3p sideways overlap would not be that effective due to comparatively large size of these 3p orbitals. One 3p, one 2p we can still understand. Somewhat it would be effective, but both 3p, it will not form an effective back bond. It would rather prefer forming a dimer, and instead it forms dimer. So back bonding I'll put across. Instead it will go for dimerization. It will form Al2Cl6 where 1, 2, 3, another 1, 2, 3, and this lone pair donating to the vacant orbital of the other aluminium atom. This lone pair from this chlorine donating to the other vacant 3p orbital of aluminium atom. So it undergoes dimerization but not back bonding. Fine. So this we have seen, p pi back bond, p pi d pi back bond also. All the effects of back bonding. The answer is 1. Now let's compare the order of Lewis acid strength in boron halides. As we have just seen that in the case of BF3 there is 2p back bond. So the extent of back bonding is more. Whereas if you consider here, it's 2p 5p back bonding, which is not that effective. So greater the extent of back bonding, lesser will be the Lewis acid strength, and hence the order of Lewis acid strength in the increasing order is least for BF3 and maximum for Bi3. As I had mentioned, if the lone pair participates in back bonding, it would not be considered present in a hybrid orbital. If the central atom is an acceptor, it has a vacant orbital, its hybridization after back bonding does not change. Here let us compare these parameters. We do not see a back bonding here because carbon doesn't have a vacant orbital to accept lone pair. Carbon belongs to the second period, so it doesn't have a vacant orbital to accept lone pair from nitrogen, while silicon does. Hybridization hence remains sp3 here, but this, as mentioned, changes to sp2. Shape is pyramidal, while it's planar, trigonal planar due to back bonding. Bond angle is close to it, slightly less than 109.5 here. Here it's 120 degree. Now planarity around nitrogen. If I consider the lone pair, it is having a pyramidal shape. So it's not planar. Whereas it's a planar molecule considering the back bonding here. Lewis base strength. This lone pair is completely available. Yes, it's a strong Lewis base. At the same time, the plus IPEC groups supplying electrons and increasing its Lewis base nature. Whereas this lone pair is not involved in this lone pair is involved in back bonding and hence not available. So it's a poor Lewis base. Thank you very much